Number 8 is a combustion analysis problem. And combustion analysis problems can be pretty tough because they employ a whole lot of different concepts and a lot of work and a lot of numbers you got to keep track of. So at the core of all these combustion analysis problems is the notion that according to the law of conservation of mass, the total mass of carbon, hydrogen, and oxygen on your reactants, or left side of an equation, needs to equal the total mass of carbon, hydrogen, and oxygen on the right side, or the product side of that equation. When we're combusting a hydrocarbon, right, a combustion reaction implies that whatever our reactant is going to react with oxygen, and because it's a hydrocarbon, it's going to produce two things every time, carbon dioxide and water. Okay, if we know the number of grams of carbon and hydrogen on the right side of the equation, we know that all of those, well, that entire mass of carbon and hydrogen needs to belong to whatever our hydrocarbon is, because it can't be in the oxygen because, well, oxygen is just oxygen. Some of the oxygen on the right side will be in our hydrocarbon, and the rest will be in our oxygen. So if we can determine the grams of carbon and hydrogen on the right side, along with what I'll call the leftover oxygen, we can figure out our chemical formula for our unknown hydrocarbon. Right? It then becomes an empirical formula problem. I always like to get started with what I think is the easiest part of these problems, and I want to determine the mass of oxygen in O2 on the left side. So in this problem, you're told that combusting 2.78 grams of ethyl butyrate yields 6.32 grams of CO2 and 2.58 grams of H2O. You're not told the amount of oxygen in O2 on the left side. You can figure that out using the law of conservation of mass. Total mass on the right side needs to equal the total mass on the left side. So we can figure out the mass of O2 by adding up our mass of CO2, or 6.32 grams, with our mass of H2O, 2.58 grams, and subtracting from it our mass of ethyl butyrate, 2.78 grams. That'll give us 6.12 grams. That's our mass of O2. We know that O2 is 100% oxygen, so we can also say that 6.12 grams of oxygen are in our O2. Once we've got that figured out, it's on to the harder stuff. So again, I said we want to determine the amount of carbon, oxygen, and hydrogen on the right side. You can do that using sort of this diagram that I've drawn a million times throughout the chapter. So we can go from grams of substance A, back and forth between grams of substance A and moles of substance A using molar mass. You can go from moles of substance A to moles of substance B using mole ratio. And you can go back and forth between moles of substance B and grams of substance B using its molar mass. In this case, we're starting with grams of carbon dioxide and grams of water. We want to know separately our grams of carbon, hydrogen, and oxygen. So that means we're going to have to go through this whole cycle to get from grams of our compound to grams of our element. Usually, the mole ratios we've used have involved entire equations, and we've used coefficients in the balance equations as mole ratios. In this case, we can use chemical formulas for compounds to give us our mole ratios. So let's get started with our CO2 here. All right, CO2 is made up of carbon and oxygen, so we want to figure out what the mass of carbon is in this CO2 and what the mass of oxygen is in this CO2. So we can go around this complete cycle here to go from grams of CO2 to grams of carbon and oxygen. So we start off here. We use our molar mass of CO2 to yield moles of CO2. Once we get our moles of CO2, we can look at the formula, or not the formula, yeah, the formula for CO2. Right, that tells us that there is one carbon in a CO2. We'll use that as our mole ratio. If we multiply our moles of CO2 by our one carbon per one CO2, our CO2s cancel out, and we'll be left with 0.144 moles of carbon. From there, it's a matter of multiplying by molar mass of carbon, 12 grams per mole, to get our total mass of carbon on the left side, or sorry, on the right side, 1.728 grams. If we go back to our moles of CO2 that we determined earlier, right, our chemical formula tells us that there are 2 oxygens per CO2. So instead of using a 1-to-1 mole ratio, instead we use a 2-to-1 mole ratio. And we'll use that to yield the moles of oxygen. So if you multiply moles of CO2 by 2 oxygens per CO2, you'll get your 0.288 moles of oxygen. I'm going to leave that there for now because there's also some oxygen in the H2O. So I want to include that and get a total moles of oxygen before I can get the total mass of oxygen on the right side. We can use a similar strategy with H2O to split that up into our grams of hydrogen and grams of oxygen. First thing, we use the molar mass to get our number of moles of water. So we divide it by 18 grams to get 0.143 moles of H2O. We can split this up into hydrogen and oxygen using mole ratios. There are 2 H's per H2O. So if we multiply our number of moles of water by this mole ratio, we'll get that there are 0.286 moles of hydrogen on the right side. Molar mass of hydrogen is 1 gram per mole, so we know that there are 0.286 grams of hydrogen on the right side. There is only 1 oxygen per water molecule, so if we multiply our moles of water by our mole ratio of oxygen in water, we'll get a different number of moles of oxygen than we had of hydrogen. We end up with 0.143 moles of O. If we add this oxygen, the oxygen from the water, to the oxygen we previously determined from the CO2, we get that there are 0.431 total moles of O on the right side. Multiplying this by oxygen's molar mass yields 6.896 grams of O. Okay, let's take a breath here. As I said earlier, right, all of the carbon and all of the hydrogen on the right side has to be in our ethyl butyrate, our hydrocarbon, because, well, there's no room for it in the O2. Some of the oxygen, not all of the oxygen, will be in ethyl butyrate. So what we can do is we can subtract the mass of oxygen in the O2 on the left side from the total mass of oxygen we had on the right side. If you do that, you'll end up with 0.776 grams of oxygen in our ethyl butyrate. As I said before, now this is an empirical formula problem. We have gram amounts of carbon, hydrogen, and oxygen. Our next step is to go from grams to moles. Again, you use the molar mass to do this. So we divide our masses of carbon, hydrogen, and oxygen by their molar masses to get moles. You end up with 0.144 moles of carbon, 0.286 moles of hydrogen, and 0.0485 moles of oxygen. Once you have your molar amounts, you divide everything by the lowest number of moles you have. In this case, oxygen provides our lowest number of moles. It's got 0.0485. If we divide everything by 0.0485, you end up with whole numbers, or at least numbers close to whole numbers. You can round. Those numbers are 3 for carbon, 6 for hydrogen, and 1 for oxygen. Since we have whole numbers here, we can use them as our subscripts. We find out that the empirical formula for ethyl butyrate is C3H6O.